Yeah, ladies and gentlemen, warm welcome to today's lecture. Today on one of the last aspects of electrical stimulation that I want to share with you, the question, when is electrical stimulation safe? And what does that mean? And is there a kind of biomarker or a parameter that is comprehensive with that? Next week, then, my trial to give you an overview about sensory feedback and how we can use electrical current to tap in there. Before I start with that lecture, two hints. One is that the evaluation period is still ongoing, and I got an email that feedback is not enough to do the analysis of data. That means I kindly ask you, if you haven't done so far, to join the evaluation and fill in something. If you already have done it and you know somebody who hasn't, then please send a strong hint into that direction. I have, again, as one Wednesday per month where I have to rush out here after the lecture to meet another meeting in the city center. This is again one of those weeks, so short questions are good. Longer discussions is something I like to ask you to postpone to next week. Then I'm again available for longer periods of time. Good. So limits of safe electrical stimulation. That's a tough one. I mean, we anticipate, we do something good when we stimulate according to the purpose, and the question is, how far can we go? And should have uploaded the paper I'm talking about. And that's the funny thing, because there have been 20 years of research, and then an engineer was hired, and his task was, can you give us a parameter? And that was published in 1992. And this really crude rule of thumb is still valid, and it was probably about 4 or 5 years ago that I've seen the first papers popping up on other methods. I don't have them with me because they're still in a very early fundamental phase, so I like to comment on that later on in the course of this lecture, but I don't want to guide you in certain directions where the community is still controversially discussing if this should be taken or not. So you get the hints, but we rely here on rock solid stuff where people agreed on. So the outline for today is on this slide, and the question at the very end is, which parameters are relevant? On which parameters should I have a look at? And we should prevent acute effects, so something that is irreversible. But we should also look on chronic effects. And the question, of course, is that true for each and everybody? And I would say my personal opinion on that is no. So depending where you are in the body, which person that is, I mean, we don't talk about healthy persons with nothing in the background. I mean, we have diseases in which we implant devices, we have traumata where a lot of stuff already happened, where probably certain agents might be in misbalance. If we think on Parkinson's disease, where people underwent a serious trauma after spinal cord injury. And I'm pretty sure that certain neurotransmitters, certain markers of foreign body reactions might be already changed a little bit. And if you add something on that, the question is, can you predict those outcomes based on mouse or rat data? Right? This is always the difficult question in the background. My dream would be some markers which you could record online in vivo, get like a traffic light, a green, a yellow, or a red, where you know, oh, I'm still in the good range, or take care, something is going on, you should lower down, and then check it out, and after 1 week, one will say, oh, it's still green, I'm fine. Or say, oops, now I'm really in the damaging range, stop immediately, we should have a look on that. This is still not yet there. This is probably a dream for the next generation to make it, to let it become true. But this is what would be nice. Currently, we mostly look retrospectively. That means we do something, and then we slice the tissue of observation, stain it, look in the microscope, and draw our conclusions. This is how it worked over years. Now, molecular biology comes in, genome has to be deciphered, and that means we have the opportunity to look on certain DNA regions and could get an idea, are certain genes switched on or switched off again, and how does that correlate with the implant, with the underlying inflammation, scarring reaction, and with that, the time frame. This is a difficult task, so certain hypotheses are, let's look, this gene might be switched on because that's good for, or this responsible for scarring, another gene is responsible for something different, and then you see this is switched on and that is switched on. You get a kind of puzzle, but it's not yet clear what I should look at. Yeah, you can have those single markers, but you have still no clue how this comes together. I mean, if you look on the properties of milk and sugar and flour, you might learn a lot, but you don't get the texture of a cream cake out of that, right? So it's a lot more that's in there, and this is ongoing research. So it's really exciting time to look at this, but I cannot give you the ultimate truth how to use that. So it's still something under observation, under research. If we look on those really old style slides here, this is how it goes, and I try to switch off the light for a second, that we have a better contrast here. If we look on the left-hand side and on the right-hand side, these are slices from cortex of the cat. And this is like in your older days when you were in the art lecture in high school. You get a picture where you had no clue about, and then your task was, please describe the picture and make a story out of that, yeah? This is something like that. And if you have no idea what you should look at, you try to describe that. And you could, for example, describe, well, on the left-hand side, I see darker grayish things, cells, which have a nucleus in the middle, and they're more or less round-shaped. And if I compare this left-hand picture to the right-hand picture, I could count probably less darker grayish things, cells, and they are no longer round, they are triangular shaped and yeah, look different, and probably I see some holes in there, or yeah, something like that. And it turns out that the cells on the right-hand side are dead or close to dead. So they are in a non-healthy state. And this is something that you can learn from those pictures. Regular cells are roundish, but they are not a circle. If you see only circular shaped cells, they are also stressed and they swell for certain reasons when they're perfectly round. If they are roundish but not exactly, then they seem to be healthy. On the right-hand side, they're no longer healthy. They're either dead or close to dead. Not good. And this could be due to metabolic stress. So this is a picture where an electrode has been placed and stimulated at a high frequency with a lot of charge. And for certain reasons, the cell did not like that. But the underlying question is, what was the parameter? Was that the charge? Was it the charge density? Was it the repetition frequency? Is there a certain influence on the electrical field? So is it the field or the voltage or the charge, or how does it come together, and how to prevent that? If we look here on the details, 8-hour stimulation at 20 microcoulombs per square centimeter over a platinum electrode, and you would either know that already by heart, or you look up on the first electrode characteristic things, you would find a table where some persons say, well, 40 microcoulombs per square centimeter is the most conservative charge injection capacity for platinum that I can imagine. We're here at 50%. So from the chemical side, the platinum electrode should be still okay. So you did everything you should do as an engineer. You stay below the limits. 8 hours, it's not that much, right? If you would have a cochlear implant, you want to hear more than 8 hours a day, probably. Yeah, but it doesn't look good. 10 nanocoulombs per phase is now an important parameter, but it does not help a lot. You know, we don't know at this point how much current, which pulse width. We see it's 20 microcoulombs per square centimeter, but we have no idea how large the electrode was. So did it cover the whole cortex? What is a needle with a tip or something like that? That means we have the parameters where I told you you should look at those, but we still have some missing information. And that's the challenge in many cases. If you look retrospectively through a lot of publications or whatever, you may not find those things that are of interest for you, because the guys and girls did the study with a completely different purpose, and so did not comment on that. All right, so we know that cells die, and the question is, why do they die? Yeah, and I recently learned from a colleague of mine that this slide is wrong. But it helps us because that is a kind of it's nearly true. So we have two main pathways for cell death. Necrosis or apoptosis. Necrosis means the cell dies. For example, because it's starving to death. So that's a kind of regular death of a cell. The cell swells first, the mitochondria undergo certain changes, and then the membrane breaks down, and if a cell membrane is gone, the cell is no longer a cell. Yeah, so the cell is dead. That's one major pathway. The second one is cell stress. If the cell is really under certain stress and finds out I can no longer survive that stress, it switches into a kind of suicide program. That's called the apoptosis. And in that case, the DNA fragments, so the chromatin pattern of the nucleus is no longer preserved. It fragments and the cell breaks down in smaller cell-like structures. It's also dead at the end, but the cause and the way to come there is different. So, and what I learned now is that there are not only those two pathways, but there are mixtures. So there's something that is now called necroptosis, which means there is a mixture between necrosis and apoptosis. This is just a repetition what I learned from a colleague of mine, and one of our ideas for a new research program is, for example, to to place cell lines on electrodes and stimulate them and try to find out when do they undergo necrosis, when do they undergo apoptosis, and when do they go in that middle stage, and is there a certain level where you can reverse that. Yeah, this is the idea. So if you're keen on doing cell cultures, and this is now the marketing part here of my lecture, and you're looking for a thesis topic, this could be one, for example. So that means we have shrinkage, swelling of cells. You have seen that in the very first slide, there are changes in morphology and probably cell density, so I did not count those cells, but that could happen if some of them die. We have less cells per unit area or volume area. And we can also have, as foreign body response, infiltration of other cells, macrophages, leukocytes, fibroblasts, depending if you are in the peripheral or in the central nervous system. And that is very important, that those two things, cell density and other cells. If you imagine you place an electrode in the brain and you're really good in preventing foreign body reaction, then you would have only a tiny little bit of a glial scar around. But that's only half of the truth. What you anticipate is that the neurons stay in close vicinity to your probe. And if so, smaller or thinner scar is good. Then you have a better transfer function between the cell and your probe. Well, what happens if the cells go away? Yeah, then you have no glial scar, but you have also no cell in the vicinity from which you can record. And this is really the second point, which has to be taken into account. Are the cells still there that I want to record? Sometimes it's even crazier. It could happen that the ion channels decide that they want to sit somewhere else. So I've seen figures from very crazy time-lapse videos that ion channels are able to move in the cell membrane. And if you have bad luck, then you have your electrode really close to the nerve cells, and the ion channels decide to go somewhere else. That means the signal is not close to your probe, but somewhere else on the nerve cell. So a lot of issues that could happen if we talk about that. What we definitely want to prevent in those issues is that we have material residues somewhere in the tissue. That happens if your material flakes off or if it gets dissolved or something like that. That means that is device failure and residues from that. And I want to exclude that mainly in biological safe stimulation. I would say that's the chemical safety that we have to consider and look on one hand side. And then the second question is, what does our stimulation do with biology? That means we exclude those pH shifts due to hydrogen ions because we did something wrong with the pulse from the real biological effect due to excitation or something like that. How to do that? State of the art is histology or immunohistochemistry. That means we characterize functional issues by staining different cells, different parameters. And this is an ex vivo method. That means you can do that with either extracted tissue by biopsies. So you push a needle into the tissue, retract the needle and try to get the tissue out of the needle and then investigate that. Or you get tissue because the animal has been sacrificed or the patient is dead and donated the ear, the brain, or something to the anatomy department. Or you have to explant something that is already in and exchange it, and you get some tissue around the probe with that. But state of the art is still, I take the tissue and I take the probe and try to separate that. Yeah? if you have a thin probe and you retract it and then you get the brain, the question is, oops, where was the probe? So either you have a large hole, then you know, oh, there has been something in there, or you have to make a marker there. For example, inject a little bit of a dye that is fluorescent, that you know that. But at the end, in most cases, you separate the probe and the tissue. That means you have created a damage in between that, and you have to make certain assumptions how good the probe was sticking in there before you pulled it out. And if you look on the probe, you will find, oh, there's still something on that. It's not that it's crystal, that it's really pristine. There are proteins, there's certain cell residues and whatever. And this is a bit of a drawback, because from a really fundamental research question, I would love to see, what do the cells do at the interface? Are there filopodia that creep under my insulation and pull on that? Is there really a fluid film that there's no contact, or are there cells that try to eat up my probe or something like that? That was again kind of a marketing issue, because we currently try to develop preparation methods that we can investigate probes and tissue together. Bifocused ion beam and scanning electron microscopy. That means we try to cut a hole in there at that place where we want to investigate that, and then we would use scanning electron microscopy to look on the interface. With all the challenges, you have to stain the tissue in a way that it reflects the electrons in a different manner. If you would take light microscopy, you can already do that with with non-very stiff materials, so polymers and thin metal films work. You need more knives, because the knife breaks out if something is an obstacle there. The main challenge is the preparation. Biological tissue is wet and squeezy like a sponge, and to investigate that, you either have to freeze it down, -70 or something like that, or you try to embed that either in wax or in a resin. And by that, you have to get the water out of the tissue and the resin in. And biological tissue has different opinion about how to get the water out and the resin in than silicon or a tungsten wire or whatever microsystem you can imagine. And that means the brain shrinks in a different percentage than your probe. Imagine you have a brain and a probe, and the brain shrinks. Then you have artifacts that might be caused by the shrinkage process and not by the original foreign body reaction. And this is really tough to separate that later in the imaging, to see what is really a preparation artifact, what is the biological cause. This is, again, something we are currently working at research. I thought it's just about the machine, to have that machine in place. But unfortunately, we found out after buying the machine that we are about the first groups on Earth who try to prepare that together on a large volume scale. And a large volume scale is probably 3 square millimeters. It's not that we can image a whole human brain or something like that. It's really small and tiny, but still it's a kind of research challenge that I wanted to share with you here. Good. Now some boring slides as repetition. What could happen if we talk about safety? And let's go to the chemical safety first, just as a repetition. If we have platinum, we have platinum plating with hydrogen. And this is not bad as such. This is a kind of reversible reaction, so we can bind it or we can release it. The only thing that we should keep in mind, if we would have really pure platinum, and imagine a lattice, where platinum atoms are sitting next to each other. And now the hydrogen or the hydroxide ions come and say, hey, I want to play with you. So, and they join the lattice. Then we have a kind of point defects, and we might get intrinsic stress by those point defects in the layer structure. And if you have listened to persons making new batteries, or talking about the future of energy with respect to hydrogen storage, you might have learned already that there's something like hydrogen embrittlement. So if you have a metal, hydrogen tends to incorporate at the grain boundaries in the structure, and this then changes the mechanical properties, and the platinum as such gets more brittle. That means, especially in thin films, if we talk about 200 nanometers, which is not that much, that's if you look on the cross-section of those films, you can see we have one grain in the film. That's really cool to see. No, not really homogeneous material, but you see there are really grains sitting next to each other in the metal. And if you stimulate, those grains might grow for certain reasons. And if they grow, they're able to grow out of the layer that you have deposited. That means they're pushing against the insulation layer, or they incorporate at the grain boundaries hydrogen, and then they get brittle and flake off. That means we have to think more in detail on that as we did before. If you have precision mechanics, let's say 50 microns or a tenth of a millimeter of a material, then you really have bulk, and it takes much longer before everything diffuses in. And if your lifetime of an implant is 30 years or something like that, you still might end up with a certain layer that's self-containing. However, if you start with something that is 1/100th of that or 1/10th of that in thickness, then your effects that you want to ignore start much earlier. And therefore we have to look much closer on that. Iridium oxide seems to be a better material, also all repetition from the electrochemical reactions, since we have that change in valence there between 3 times and 4 times positive depending on the voltage. Therefore we can deliver more charge. I haven't heard about iridium oxide embrittlement so far. There are two options. Either it does not happen, or persons did not look it up. And I'm still not sure what the truth is behind that. Probably I can tell you or somebody else in some years if we have found out something. That's currently another research direction we're looking at. What really happens in those thin film metals under stimulation? Do we see it? Are there certain effects on that? And what can we do on that? And if we do something really wrong, then we are out of the water window. That means we generate hydrogen gas, we generate oxygen gas. We might generate platinum tetrachloride. This is a really mean thing that's dissolvable. And it increases the surface of the platinum electrodes. That means if you damage your electrode in one half of the stimulation pulse, then it deposits on the other half. And if you would do a characterization, just an overview characterization, let's say, oh, my electrode looks really good, nothing changes. And then from one pulse to the other, you say, oh, no, it failed. That's then the point where really the interconnection line or whatever has completely corroded. So you might have an electrode, but there's no contact any longer, or you have left your whole surface area or something like that. That's one of the disadvantages of platinum, that it's really hiding a little bit its corrosion with that mechanism. And if you would do it even worse, then you could oxidize organic molecules. And this is nothing we want to do with electrical stimulation, that we jump into whatever metabolic circuit and oxidize here whatever is around. We can find out, if we don't look on the detailed electrochemistry of the electrode, but look a little bit in the vicinity, we find that we have a shift of the pH value by that, hydrogen concentration, ion concentration. And this is not only that acidic environment is probably not that good for survival of cells, but we also alterate the nerve excitability. So if we have monophasic pulses that change H+, and by that also reactive oxygen species, we trigger mechanisms in the vascular system that there is a vasoconstriction, for example. I've seen 2 years ago a really cool video from a colleague of mine who did this after retirement. He put an electrode on the brain with a high-resolution image focusing on the blood vessels. And if you stimulate monophasic, you see, due to those local changes, that you have vasoconstriction. That means the blood vessels really disappear from the camera image, while they stay at the same diameter if you have biphasic stimulation. You can do a lot on that, but sometimes you don't consider that. That's the challenge there. You do something because somebody told you, you read something about that, and then you don't read further and don't experience those effects because you closed the brain or whatever. That is the pH value thing. The dissolution of electrodes is also an issue which should be considered, just to make sure that they don't dissolve. One measurement method that has been established is that you stimulate electrodes in vitro in beakers in salt water, billions of times, and then you investigate the water. Not only the electrode, but you investigate the water if there are solvents in there. Since the detection limit of most of the machines is under the amount of platinum that might have been dissolved, you play some tricks, so you evaporate a kind of water that, you know, I have now 10 milliliters, I cook that down to 1 milliliter, that's then factor of 10, I go to whatever mass spectrometer. If I find platinum, then I have to divide that concentration by a factor of 10 or something like what you did before, and then you can find that out. That's established worldwide as a method to check out, do I have dissolution or not. If people don't want to do that because they say, well, you know, there's so much literature, I just stay below the limit, persons quite often take a safety factor. Yeah, say this is the state of the art in the literature. I take a safety factor of whatever 3, 4, 5, and then I should be safe. And now we come to the hard thing, the relevant parameters. We could imagine that it's the charge. The more charge I inject, the more I change something on the nerve. We can probably agree. Depends how much charge per unit area we have from the dissolution effect, but also I think if I would take 10 charge carriers and I distribute them over the whole body, it's different than if I would take 10 charge carriers and concentrate them on a certain nerve cell. So that means the charge density per phase is probably also a good parameter. And for sure, it depends if I do this once, single twitch stimulation, or at 10 kilohertz for 24 hours a day. So that time and repetition frequency is also an issue. So what would a scientist do? Scientists would go probably to PubMed as research database in the hope that you find both the engineering journals articles and the medical journal articles in there. And if you look on that, you find different opinions. So, and the question is, how can we come to so different opinions? So if you would ask Nick Donaldson, he would say 40 microcoulombs per square centimeter geometrical area is the safety limit. If you go on, and Timothy Rose and Lois Robley have passed away, so you cannot ask them any longer. They have reported in their publications it's between 50 and 100 microcoulombs per square centimeter geometrical area, well, which is close to 40, so we're still in the same order of magnitude. But you find others from Brummer and Turner, and they said we take 400 to 500 microcoulombs per square centimeter. That's a factor of 10. Yeah, but they say real area. And if you have to read through a lot of lines before you recognize with real area, they mean the electrochemical active area. That is, you check out, you don't measure the area with a ruler or a microscope, but you take electrochemical measurement methods to include the roughness of the area. That means if you have small bumps there, they contribute to the surface area, and it's like you would have, let's say, a piece of cloth that is very wrinkled, and then you would take a solder iron and an iron and iron that, not a solder iron, iron that, and then you'd say, oh, this area is much larger, something like that. The tricky part of that is that you do not, by this very simplistic view, you don't get the whole truth, because if you have shallow surface roughness, you would be able to access every point on the surface. If you would be a water molecule, for example, so imagine a water dipole. But if you would have very narrow, very deep holes in there, there might be water dipoles deep on the ground, and if you change something, they don't have the time to come to the surface. Means if you have too high surface roughness, you have a kind of diffusion inhibition there that where part of that roughness does not contribute to your surface effects. So it's not that easy. My way to approach that is to try to stay to at least 20% from the safe chemical borders. I could say, well, I have no idea if this is good or bad, but I'm away from the critical voltages or current densities. The electrode area is not yet considered with that. That means there might be some edge effects in very small electrodes and very large electrodes that are not yet considered. The pulse width is not yet considered. You know, we're talking here about electrodes, and in the easiest way, the electrical equivalent circuit model is something like a capacitor and a resistor. And if you remember the charging and decharging characteristics of a capacitor, it takes a time and then it stays constant. It goes to an asymptotic value. And if we would compare very short pulses, we would say, oh, we are in the early part of charging, kind of linear. Yeah? It's completely different to compare that to very long pulses where we might be already at the asymptotic value and still try to push something in there, even though the total amount of charge might be the same. Yeah? It's amplitude times time. But the kinetics of those reactions might be different depending on the amplitude and the voltage that we get with that. Repetition frequency is something, tick, tick, or a kilohertz, something like that. And of course the question, how long? 10 seconds, a minute, or the whole day. So, and there were a lot of very, very cool fundamental scientists, physiologists, electrochemists who did a lot of studies. That was all. If you look on those numbers, in the 70s, 80s, and early 90s, and if you would look up their affiliations, you will find out they seem to group around Southern California. And the reason for that is that one of the centers which investigated the use of technology for restoring hearing, cochlear implants, also fundamental investigations on auditory cortex, was located in that area of the world in the 70s to 90s. Doug McCreary is still with us. He celebrated his 80th anniversary last year. I was one of the guys who was around there in that ceremony. It was really moving to see him, and really crazy guy. He submitted his 2 days before we had that celebration meeting in California. He submitted another research grant because he had some ideas, and asked us to keep our fingers crossed that he passed through and is able to continue with research. That's probably the difference between the US and here, that you can still submit research grants and are still affiliated at those ages there. And they tried to get some grasp on their data to those days. They did a lot of studies here, and they, as in the first slide that I showed you, they tried to assign numbers to dead neurons and to neurons that haven't died. And they printed that in a diagram here, where they said, well, this is with no injury, the others are injured, and they had here 50 hertz for 8 hours in those examples. And they found out, well, the large electrodes were rather at high charge and low charge density, while small electrodes cannot deliver that much charge, but the charge density is higher since they are small. So that is upper left, lower right there. And of course, they're intermediate states, but like in many classification tasks, you want the ideal thing would be to draw a line, to have a linear classification between one group and the other group. Linearity is an issue here. If you look carefully, you see that there are double logarithmic axes here. So we have x and y axis on a logarithmic scale already here. And for certain reasons, I don't know why, they hired an engineer, Bill Shen. It's also still Rob Shen. He's already still around, now heading the institute which Doug McCreary was heading before. And let's say the father was the former boss of Doug McCreary. That was William Agnew. That's kind of a line of those researchers who stuck to that safety question. And they did those experiments, and was more an heuristic approach. So let's group data somewhere and find a description to separate dead neurons from living neurons. And Bob Shen came out with his Shannon model for safe electrical stimulation, and we're talking now about biological safe stimulation. I mean, cells do not die. In a worst case scenario, and that has been, well, that was the first shot, and later on came out that the worst case scenario, you can make it a bit more sophisticated. That was published in 2016 by Stuart Kogan and Pasha Takmakov and Kip Ludwig and Christian Welle there. But the thing is, if you take a double logarithmic display, you can assign the charge density to the charge with a linear factor. And this is then the safety margin. You can rearrange that and find out that there's a certain dependency if you take a round electrode between that factor. And the K factor is the safety margin. And to be in a good distance to that, you should take the K factor at 1.5. That's completely heuristic. There's no scientific reason behind that. It's just arranging data and trying to get an equation out of those data that helps us. And you can imagine that this is currently under discussion. You know, we are much further now in understanding of things, and we try to assign biological causes to that relation. But unfortunately, we are not yet there. What can we draw from the Shannon factor? That is the question here. And he did. That's all stolen from his paper that is uploaded on Ilias. And he take short pulses, 10 microseconds per phase, and long pulses, 1 millisecond per phase. And this is here the maximum amplitude that you could get, the maximum charge, and the maximum charge per phase. And it turned out that it's not the area that we should consider for easy estimation, but the perimeter. And especially for short pulses, if you are a bit involved into electrical engineering, at least I have an idea about field lines that are somewhere, and field lines always go perpendicular to metal surfaces. That means if I have an electrode and this electrode is placed in an insulator, I would have discontinuities between the insulator and the electrode area. That means I have a field concentration just here, which is the perimeter. That means the first place where those charge transfer processes occur is the perimeter. If you would increase the pulse width, then it takes much longer for the charge to go somewhere, and then it takes the whole electrode area. But if the pulses are relatively short, many of the processes occur at the perimeter. And therefore, it makes a kind of sense that the perimeter here has a linear relationship to the maximum charge that I can deliver and not the area. That is an important issue, and a lot of persons played around with the shape of electrodes. I mean, if they are handmade and you would take a pair of scissors and you have to cut something, you would probably stick, or you need to stamp them out, you would probably stick to disk. That's the easiest thing. When microsystems engineering got the first round of getting famous in the 90s, a lot of persons played around with the surface. There were kind of Vathel structures to get more discontinuities. The first example was a golf ball. Yeah, you have these golf balls. They have dips on the surface to make the ball more stable and faster. And this was the first fractal structure in cardiac pacemaker electrodes, that this structure was copied, and it was copied everywhere. It was copied on motorcycle helmets, it was copied on cardiac pacemaker electrodes. No, I don't make stupid jokes here. We have in the Palatines, we have that Duppe glass, that's a drinking glass where there are also those dips in. This is not fractal, that came from earlier times, and the story says this was invented by a butcher because he wanted to drink, and having those fatty fingers, the glass slipped away, and so he made a glass with dips in that he could better grasp at. That has nothing to do with fractal structures and safety and electrical stimulation. But that was the first fractal structure. Then there were kind of grids overlaid on the electrode to have more, let's say, surface perimeters on given areas. And then that disappeared due to other materials that had higher charge injection capacities, where you're still not yet at the border at regular working times during stimulation. Yeah.
Can we keep the parameter constant and decrease the area?
I show you a slide on that. You could, if you would have a kind of flower shape, then you would have more perimeter at smaller surface areas. But you might run into problems if you go 250 microseconds pulse width towards that, for example. Then you have also the area effects, and then you would get less charge over that. And then it's a balance. You know, you want to have the safety margin, and in most cases, the electrodes are quite large for safety reasons, and your need of selectivity is relatively low. That means you're twice on the safe side if you make the electrodes larger. And in the other cases where you need high spatial resolution, then you could play around, but sometimes manufacturing limitations determine the shape. They say, okay, if I have to weigh this advantage versus that disadvantage, I'll go that way, and this quite often simple shapes. So, as the third repetition for today, again, so you see this is important, all the different parameters, also pulse pause relationship, repetition frequency, things like that. In many cases, the repetition frequency is nothing you can really work on. I mean, if this is a cochlear implant, you have to stimulate according to given paradigms to get the best hearing perception. If I grasp something, I cannot make a pause in between. Yeah, so it really depends how far you can modulate those frequencies. In certain cases, there are applications that work, like in deep brain stimulation, Parkinson's disease, where people switched between 60 and 130 hertz. There are now some investigations where they prove that 60 hertz are good. But my strong belief is that those repetition frequencies came out because there was a device on the market which by chance had either 60 or 130 hertz, and it worked. And then persons stuck with that, and when it works, don't ask why. Yeah, so probably somebody finds out in some years from now that 180 hertz or 16.6 are much better. I have no idea, but sometimes you are in that range where the established frequency is there as state of the art, and then you stick with that, period. What really thrilled me was that picture here, where you see those bubbles or the cells around, or vacuoles. That means there is a kind of void formation in the tissue. So that means something must have happened that damaged that tissue. And if you look on that hole where you find the word tip, and you imagine that was a tip, sharp tip, over which current was stimulated versus a counter-electrode. I would say what you see here as orientation of those vacuoles in the shape and distance looks to me like isopotential lines. If you would have an electrical field from a tip electrode going like rays, then you would have isopotential lines perpendicular to the field lines. And if we look on that, and I would say this was the tip here, and that tip went somewhere over current source versus ground. I would say, well, doesn't look like we have here some field lines. And then these cells look like lying on isopotential lines here. Yeah, Friedrich? No. If you, it could be, you're right, but tissue is not really like a solid state body. Not like, I think you have something from the mechanics in mind where you put something in, then you have stress distributions. If you would insert an electrode slowly enough to visualize that, you see that the cells really move apart. And if you wait for a certain time, and this is here a chronic experiment, nothing which is a minute after insertion, you really see that the cells rearrange. So I would not, it could be, but I don't believe in that, since I've seen different movements of cells. They're even if we talk as a solid, if we talk about solid tissue, it's still loosely coupled from the mechanical point of view, and it slides a little bit away. So I believe that this is really on the electrical field. And this was again here 10 nanocoulombs per phase. Unfortunately, there's no area here that you have an idea what charge density it was. But I think this is something where we should keep our mind on compatibility issues. In the peripheral nerve, we have the, how to phrase that, we have the challenge that the peripheral nerve lies in soft tissue. That means we have no protective shell, since the bone is in the middle, for example, and the arm and everything is around, and if you implant something, there's no place where you can fix it but the nerve, because you want to have your electrode in no relative movement to the nerve. The only way to achieve that is to fix the electrode with the nerve. And if you do so, and you look on that early slide, you can see two wires, and those two wires are connected to two rings, and these rings are kinked. I have no idea which person came to that stupid idea, because if you have a piece of metal and you kink it, it gets really stiff. Yeah? That means if you pre-shape it and kink it, then it has no chance to change its position without a lot of force. And if you do that around the nerve, it's like having crocodile clamps on the nerve. And if the nerve swells, the nerve is the weaker part of that. And if it swells, it puts pressure on the electrode. The electrode, as a reaction force, puts pressure on the nerve. And if there's continuous amount of pressure on the nerve fibers, the myelin sheath breaks, so it just goes away. If you would take that picture on the whole nerve, it would press on everything that is inside the nerve. There are blood vessels inside the nerve who supply the nerve fibers with oxygen. So if you occlude those blood vessels, the amount of oxygen which reaches the nerve fibers decreases. So we have a kind of hypoxia there. And that doesn't sound very good. That was one of the reasons, due to those very heavy metal designs of the early days, that cuff electrodes got a bad reputation, that they might damage the nerve. That's true, but if I take a very thick needle and would poke it somewhere else, it would also damage something. So it's always that relation of how to implant that, where to implant it, and how to fix that. And then we have the influence of activity, and could see that different stimulation, repetition frequencies causes different changes in the activity and the thicker nerve cells. Here it's on A alpha components of a compound signal, and unfortunately there's another alpha here on the x-axis which does not belong to the A alpha component of the signal. That means if you have relative values here, you see that the changes are more severe the higher the repetition frequency is. And with that mass of different publications and different data, there was the time around between 1995 and 2000 something, guess 2005, 2007, where one group in Belgium said, well, we know now a lot of things about cuff electrodes, and that was the time where persons spoke loudly about, can we restore vision with electrical stimulation? And one group in Belgium, Claude Ferrat, Jean Delbecq, they said, well, our approach would be to approach the optic nerve. The question was where to approach the nervous system for vision restorage, and there were more or less three schools. One school was, let's go to the visual cortex. Another school was, let's go into the eyeball and interface with the retina. And the third school was, let's take a cuff electrode. And there were all good reasons for every approach. And their chain of arguments was, they say, well, we have so much experience with cuff electrodes in the peripheral nervous system so far, why not taking that experience and transfer that to the optic nerve? The challenge was their cuff electrode was still precision mechanics. So we had, and I have to refer you to the last lecture on selectivity, they had either 4 contacts around the perimeter, or in the highly sophisticated version 2, 8 contacts. And this has been wrapped around the optic nerve with 1.2 million of fibers. Quite challenging, right? To get something meaningful out of that relation. They had 2 approaches before I come to that picture here. One approach was the really tough one. They penetrated the skull base and went through the skull base to the part of the optic nerve close to the chiasm where the 2 optic nerves from both eyes cross. Advantage, you have no outer thicker layer around the nerve, no dura or things like that. Disadvantage, you have to cross the skull base. Really tricky thing, you know, if you break your skull base in an accident, there's always the risk that the outer shell of the brain, the dura, is damaged, and then you would have leakage of cerebrospinal fluid, and so not very appealing approach. They implanted an electrode with 4 contacts there, and then they discovered a second approach, which sounds also a bit awkward. So you take out the eyeball and stretch a little bit unless you reach the optic nerve, and then you can place a cuff electrode around there. Sounds easier, sounds not really appealing, but easier. But you still have a kind of harder skin well, skin, not really skin, but something dura-like around that. Then you have 8 contacts, but you have that insulating layer around. That means at the end it turned out the 8 electrodes with that approach had a similar selectivity than the 4 electrodes being a bit closer. And it turned out it's not sufficient to restore vision such that you can do something with that in a real-time environment like crossing the street. Yeah, it took, they had an experimental setting where, and the thing was they went immediately to humans because they said there have been so many animal experiments on whatever, we need the human to find out if a human can see with that. And they passed the ethical committee with that, implanted 2 persons, and put them into an experimental setup where you had a checkerboard, so chessboard, 3 by 3, and the person should say, is this a banana, a coffee mug, or a table, so plate on the table on the chessboard. So which object and where? And it was like in early science fiction movies with aliens. Those stimulations generated phosphenes. Phosphene is the technical term for visual perception, and this could be, some persons describe that at, I see a green pea at 11 o'clock in a distance of 3 meters. I say, well, if you stimulate me that way, I see a shape of a shoe being there. And that means you have to note that, you have to assign that, and then get a clue, how can I bring those perceptions into something meaningful? And for those patients, it turned out that the best was that the camera makes a black-white tone picture out of that you just have the parameters of the object, but that meant those persons scanned the whole environment. That resembled me immediately on Battlestar Galactica, if you know that old-style science fiction movie from the 80s. Yeah? That was really looked awkward. And it took between 60 and 120 seconds before such a person could say, this is a banana lying on A1. That means it was nothing that could be transferred really in real-time vision that's beneficial for increasing the activities of daily living. I would say one of that was hard research work, and we can all smile on those results now from 20 years backwards, but it was really groundbreaking 15, 20 years backwards from now. And another groundbreaking thing was that Claude Ferrat brought all the knowledge from the recent years in that graph. That's still that Shannon graph, yeah, with charge density on the y-axis and charge on the x-axis. But Claude did something else. First of all, he put that line, Shannon's charge limit, k equal to 1.5. Then he said, well, that's only half of the truth, because if platinum is solving, if there's platinum dissolution, I don't want to have that. So the horizontal line is platinum corrosion. And printing in the old data from the 70s and 80s and 90s, it turned out that it's not amazing that some of those cells were dead, because that was above the limit of platinum dissolution. That means we probably might have already created bubbles in there or whatever. So that was one thing. And it turned out that the area of the electrodes, which are the diagonal lines there, is also influencing the outcome. And it's good to display also the area of the electrodes. And since this group in Belgium had only one size cuff electrodes, we see a lot of data here on that particular line. Those were the experiments that they performed on those, and for me, not very surprising, they found out that their chosen parameters are not damaging the nerve cells. Yeah, that's good. If you want to criticize something, then I would criticize that these are data on the optical nerve axons, while all the other data were cortical stimulation. When we look into the anatomy textbooks, we find out the optic nerve is assigned to the central nervous system, since this is a brainstem nerve. So we are still by definition in the CNS and not in the peripheral nervous system, but I would say it's a difference if you stimulate axons from stimulating somata in the cortex. But I recommend if you do something, safety issues, look back on those things, check out if there's recent literature on that, and make your clue how to proceed. There's still no gold standard on chemical safety, on biological safety. This is the best what we have, but it has its limitation. On top of that, if we talk on biological safety, we should also include changes in the transfer function of nerves due to the electrical stimulation. I mean, the first thing is keep the nerve cells alive. But the second is, what if we would change the complete neuronal network by the stimulation? You could say, oh, this is by the therapeutic effect. Yeah, this is one option, but there might be other applications where you do not want to change that. You want to change something completely different. And if nerve cell A talks to nerve cell B and the language changes due to your stimulation, that probably does not reach nerve cell C where you want to have an effect. And this is the so-called stimulation-induced depression. If you stimulate, you may find out here, and the details are in the figure caption, that your response to your same stimulation amplitude decreases, not because scar tissue is growing, but because of changes in all those neuronal networks in the vicinity over days. We see here the black filled dots are day 0, and after 31 days, we have a significant drop in response due to changes in the underlying network. The question is, does that saturate? So if you know that, and you cannot do anything against it, and you have a saturation level that is all rightish, then you can deal with that, but that would mean that you need a kind of recalibration after a certain period of time. And the important thing is to take the safety margins in mind, that you do not just increase the amplitude because you want to get the same output, but you have to have some safety limits for the chemical thing behind that. And that is a kind of safety architecture in many devices that the medical doctor or the health personnel can readjust parameters. For example, in cochlear implants, you normally go once a year into a cochlear implant center and check your hearing capabilities with a cochlear implant, and then depending on whatever plasticity or changes, further degeneration, the parameters are adjusted. Adjustment means, in many cases, just increase the juice that you give. Yeah, so current amplitudes get higher. But there's a safety architecture in the second layer behind that you cannot go over a certain limit, which is then the safe, let's say, chemical safe level and maximum tolerable biological level that you have. Very important in the design space that you do something that really limits that, just in case the rehab centers did not read the instructions. So what is that? Completely forgot that slide. I was just in mind on the next one. So response can change. I think this is what this slide says. If you increase stimulation, then the output can increase. That is good. But the question is, do you want to have that? Yeah, how far do I want to go? Can I get some overshooting response if I overdo it with my stimulus? So is there kind of positive feedback that drives my system to a point where I don't want to have that? And the excitability can change after continuous stimulation. It comes to that stimulation-induced depression of neural excitability. That means it could happen that neurons do no longer respond that well due to that stimulation here. And we have relatively low values here. If we look 26.5 microamps or 4 nanocoulombs per phase is not that much. For the auditory system, 50 hertz is also not that much, but that means that we have some underlying mechanisms somehow that downregulate the excitability of the cells. So to summarize, or to try to summarize, I hope you have now the same feeling than I have. So their safe stimulation is really not that you can say safe or non-safe. It really is a really complex topic. All those data here have been mainly on cats, healthy cats, healthy subjects. I mean, even if you're blind, the nerve is still healthy. If you would imagine you are in a degenerative disease, like Parkinson's, means it's not that the nerve as such is healthy, but you have a completely different situation there. That means what could be healthy in a cochlear implant or safe is probably not safe with respect to that disease or that patient or whatever. You know, there's so much variability between humans that we are not able to say this is red and this is green, this is good and this is bad. So it must be something more sophisticated, which is not yet there. We have dependencies on the design and material parameters here, like active surface, diameter, perimeter, surface roughness, pulse width, repetition frequency, amplitude. But the biological reactions, so the root causes, why does something happen? Do we see it on a single gene? So if we say this gene is switched on for longer than 3 days, something is going wrong or not. It's not yet there, and I think we will need much more time to understand all those dependencies, what happens there, and I hope that somebody will find certain parameters how you can measure that in a way that you get better personalized limits that help to get those implants work much better, and probably also more on the boundaries if needed. Yeah, and with that, come to the educational targets, and I always recognize the later the lecture is, the more important the educational targets become if we get closer to the exams. So I'd like you to be able to discuss the concept of safe electrical stimulation by your own, so that you know certain aspects and you can weigh them. That helps if you talk to one of the others and you ask each other nasty questions. That helps to get you to the point where you're able to phrase these different points. And that's important for an oral examination, that you can phrase answers. I mean, that's different to a written exam, where the question is, what is 3 times 4? And then you calculate and say 12. Yeah, that's kind of more the style of written exams, where it comes to a certain answer, to a certain statement. In oral exams, it needs the knowledge of details and parameters, but it's more about phrasing situations, being able to discuss those things. You should, of course, have those material reactions, not all of them, but knowing that platinum and hydrogen makes PTH, that there is something like platinum tetrachloride. I think there's a maximum of 5 or 6 equations here on the redox processes. And if you know them halfway, I don't need all the electrons that hop here and there. If you have a photographic memory, that's fine, then you can write that down. But if you are more in favor of saying, well, there's platinum hydrogen plating, and this brings us back and forth that material, I'm also fine with that. So up to you how you memorize that. What you should have here is that relation between electrode and the stimulation parameters, that you can mention those and discuss them a little bit, and that you know some of, let's say, some of the most significant biological reactions after stimulation. And with that, you're on a good way towards understanding and knowledge. So with that, I like to close for today. Next week is about sensory feedback. I've already some ideas what I like to show you. I still have not that much of ideas where I find the data that I do not yet have. I have some ideas what I like to show you. I'm still looking for good pictures on that, and I would be very happy to see you next week again on that sensory feedback lecture. Like to remind you again to participate, please, in that evaluation stuff, even though it's a bit time consuming, but it really helps us all to get that feedback from your side. And with that, I now really close and wish you all the best for the following week. Thank you.